All right, well, we left off, we talked about the interpretation of the slope. I think that was the last thing we talked about on Wednesday, so. Okay, so let me, I'm going to pull up a Word document and I'm going to just type things out, and I'll give you a few options here. We'll do a clicker question. Let me see if I can get Word fired up here. Okay, so the way this is going to be is we're going to say, imagine we have a linear regression model. Okay, and we'll say the scatter plot, let me make this larger and visible. Okay, so imagine we have a linear regression model. The scatter plot shows that a linear relationship is appropriate. Okay, the best fit line has the equation. Okay, and so for this we will say height, we'll say expected height. Now, can I just write height hat is equal to 1.25 plus 0.45 times days. Okay, the x is days since planting, and y is height of the plant. Okay. All right. So interpretation of the slope. Is this okay? No, we can fit all this here. All right. So this is what we have. Okay. So we're gonna have a few options for what the interpretation of the slope is. Okay. So we're gonna say the height increases. Height of the plant is in centimeters. Okay, the height increases by 0.45 centimeters for each day that passes. Okay. B. Oh, I guess Word is with the emojis. Okay. So height increases by 0.45 centimeter each day that passes. We will say if the height increases by 1 centimeter, that means that 0.45 of a day has passed. C will be if we increase the number of days since planting by 1, we expect the height to go up 0.45 centimeters. And then D will be if the height changes by 0.45 centimeters, then the days increase by 1. Okay, so let me see if I can get this all to fit in a thing that I can screenshot or copy into. Oh, I have to turn on the clicker. Okay, let's do that. Okay, if you want to talk to your neighbor, go ahead and talk to your neighbor about which of these is correct. Now, a lot of them sound kind of correct, but only one is actually correct. So let me just paste these over here. Okay. Okay, let's get your clicks in. If you haven't clicked your remote already, get your clicks in. Okay, let's take a look here. Okay. And the correct answer here is C. Okay. So the reason why A is not correct, it sounds very good, but the reason why it's not correct is because it just talks about the height increases. So the key here is that we have to write we expect or we predict. Okay. So we can, if A had said the expected height increases, then that would be correct. Okay, if we say the expected height or the predicted height, expected or predicted height increases, by 0.45 for each day that passes, that would be okay. But to say that the height actually increases by 0.45 centimeters each day is not a correct statement, okay? Again, when we create a linear regression model, it's a model that shows what we predict or what we expect. It's not showing the actual relationship between x and y, okay? So this is not correct because this is about the actual relationship. So if A had said instead the expected or the predicted height, then it would be correct. And so C this is correct, even though the wording is funny, right? If we increase the number of days since planting by 1, this is just basically saying if we increase the x variable by 1, okay? And even though it sounds strange to say something like that, basically if the number of days since planting goes up by 1, then we expect the height to go up by 0.45 centimeters, and that is the correct interpretation of the slope there. All right, is this okay? All right. We did not talk about the intercept though, correct? Okay. Sometimes, all right, so the intercept. So if we have y hat is equal to a plus b times x, then a is the intercept. Okay, a is the intercept, and the interpretation is our prediction for y if we plug in 0 for x. Now, sometimes it makes sense to plug in 0 for x, other times it does not, okay? So sometimes so on the previous page, we said something like the height, the predicted height or expected height hat is equal to, what did I say? 1.25 plus 0.45 times days. Okay, so in this case, our intercept is 1.25, and so this means if days equals 0, then we predict the height of the plant to be 1.25 centimeters. Okay, and that makes sense, all right? If that just means when you first put in the little seedling or whatever it is, it's, you know, maybe 1.25 centimeters tall, and that's fine. That's our prediction for the height of the plant if the number of days since planting is 0. Okay. On the other hand, we might have something like, if we're talking about the weight of a snake based on its length. Okay, so if we're talking about snakes again, and we have something like predicted weight is equal to, you know, I'm just making up numbers, 12.4 plus, you know, 9.7 times length. Okay, then in this case, the intercept is 12.4, and the interpretation, the direct interpretation would be if length equals 0, then the predicted weight of the snake is 12.4. Now, that does not make sense to have length equal to 0. You cannot have a snake with length 0. Okay, that is literally no snake. So, so it is not possible to have a snake with length 0. Okay, so in this case, you know, the intercept does not have a practical interpretation. So, you know, depending on your situation, you know, the direct interpretation of the intercept is what we predict y to be, okay, if we plug in 0 for x, but again, sometimes it doesn't make sense to have x equal to 0. All right, let's talk a little bit more about linear regression and some of the things that that go on. Okay, so you can switch the variables between x and y if you want. So you know, you have, let's say you have, I don't know, length over here and weight over here. Okay, and you got some kind of trend line here. for the, we're talking about whatever it is, snakes or whatever, okay? Now, so in this case, x would be length, and y would be weight. Okay? And perhaps you have y hat is equal, I forgot what I said on the previous slide, 12.4 plus 9.7 length. Okay. If we wanted to, we could swap, or not swap, I should say, we could make x the weight and y to be the length. Okay? And what does it mean in this case? If we make x the weight and y to be the length, that means we are trying to predict what based on what? So this time, rather than, it's like over here you only have a ruler or a measuring tape, so you can measure the length, but you don't have a scale, and so you're trying to figure out the scale. Over here it's just the opposite. It's like we have a scale, but we don't have measuring tape. And so if we wanted to, we can say, well, if I'm given the weight, can I make a prediction for the length? Okay. The thing is that when you swap something like this, you cannot just use algebra and move things around. Okay, you cannot just say, okay, well now I want to solve for length in terms of y. Okay, that you have to redo the calculations for the slope and the intercept. Okay, so do not take the other equation and solve for x, okay? You must recalculate slope and intercept. So you know, right here we said the slope is equal to correlation times sy divided by sx. You would have to redo this, and you would get, this time you would have predicted length is equal to, you know, a plus b times weight, okay? And so now that you have swapped sy and sx, so over here it is r times sy is the weight, s weight divided by s length, right? Over here, now that x is weight and y is length, this slope here is r times s times the length, not times length, the standard deviation of length and s standard deviation of the weight. Okay, it's still sy over sx, but we have changed which one is the y and which one is the x. Okay, and you would have to redo the calculations that way. If you just try to solve for what length is based on that, you'll get a different value. That is wrong. Okay, are there any questions on this? Okay, we're good. All right, let's see. Okay, we have a few So conceptually, you can think about just maybe some big, the conceptual idea behind linear regression. Is that, you have, let's say we have data that is, a lot more spread out, okay? Something like this, okay? The regression line, we can think of it as what we're doing is we're trying to link up average values of x, okay? So not average values of y for different values of x, okay? So you can imagine I'm going to take a slice, I'm going to say here's my x, and I'm going to kind of take a slice here. All right? And then so inside my slice I've got kind of like these 4 data points, right? I've got this data point, this, and this. And so among these, the pieces of data inside this slice, I would say, okay, my mean goes right here, okay? And I could say, all right, here is, at another location of x, I'll take another slice of data here, all right? And I say, okay, let's look at the data points right here, and we're going to find the mean of these 4 data points. And maybe it's something right there. And the idea is we're kind of doing something like this across all of the data points. We're taking different slices and we're finding the mean of those slices, and we're trying to find a line that runs through them. Okay. So our regression line. Tries to model the relationship between x and the mean of the y values at that x. And so that's why when we say, we've got y hat, because this regression line, y hat is a plus bx, what we're saying is that it is the relationship between x and y hat being our prediction. This prediction is trying to be the mean of the values for a particular x, okay? So our prediction of y is, I'll just say trying to be the mean of the y values for a given value of x. And so, if you were to take another statistics course, then you would try to model the errors around the regression line as a normal distribution, which we'll cover later on in our class here. Okay, let me give you a few warnings about linear regression. Okay, so we gave you some warnings for correlation. Pretty much those same warnings carry over when we're talking about linear regression, but they're even more so pronounced. Okay, so warnings about linear regression. So regression it's an excellent tool, and statisticians like to use regression, and it has many applications. But some people also, you guys can learn regression here, and it's tempting to try to fit linear regression models to all sorts of data, and that's fine, but we have to be careful. Okay, so number one, the existence of a linear relationship does not mean there is a causal relationship. Okay. So if we create a plot, I think an article just came out about the consumption of diet drinks, diet soda, and risk of stroke. And there seems to be a link between, or not, I don't even know about if link is the right even word to say, but just in the study, what they found was people who drank lots of diet drinks tended to have higher rates of stroke than those who did not drink diet drinks. Okay, and I don't know if they did linear regression, but if this was diet soda consumption, and I don't know, stroke risk, I don't think, well, maybe, I doubt it was linear regression that they did, but let's just say they did this, right? Diet soda consumption and stroke risk, and basically the study says there's people who drank a lot of diet soda tended to have strokes at a higher rate than those who didn't. Okay, we can't jump to conclusions about saying, okay, well, diet soda is the cause behind the strokes. There could be thousands of other things. It could be people who choose to drink diet soda may be more likely to have, I don't know, certain other health issues, who knows, okay? And maybe that's what's compelling them to choose to drink diet soda. We don't know, okay? So they could have already been at an inflated stroke risk and things like that. I mean, there could be a cause and effect relationship, but until we start forcing people to drink diet soda and study the effects of that, we cannot make a cause and effect relationship. Okay. Okay. So this is all, correlation is not causation. Same thing goes along here. Okay. And then outliers. Again, outliers totally mess things up. Okay. So with outliers, you might have a cloud of data here, okay? So let's say we were measuring people's shoe sizes. Okay, so let's say we did shoe size versus annual income. Okay, we should see no relationship. Well, there might be a relationship because of gender wage gap stuff, but let's just say that there wasn't, okay? And we'll say shoe size and annual income, we would expect no relationship, right? And okay, so this is your thing. Your linear regression line should look something like this, right? This is kind of probably what it should look like. Maybe, okay. Let's say Shaquille O'Neal entered your data set, right? He's got very, very big feet. He also makes a lot of money. So his data point would be somewhere up here, okay? So this is Shaquille. You guys know who he is, right? Basketball superstar. And now on TNT, okay. With the rest of the NBA commentary crew, okay. And and then so linear regression will try to accommodate this, and probably the line will now go something like this. And then so now you have this definite relationship, or you have a large slope seeming to indicate that as shoe size increases, you know, the slope would tell us that as if we add 1 to shoe size, your expected annual income goes up, you know, this amount. Slope is now positive, and so that's not true, right? Okay, so I think in our study we would probably want to exclude Shaquille O'Neal and say, you know, we want to study normal feet and regular people. Not that Shaquille is not regular, but he is an outlier, okay? So there we go. Okay. So you have to be careful about outliers. All right. Another one is extrapolation. Okay. Extrapolation basically is the idea of continuing your regression model to places where you have not collected data. Okay, and basically the warning is do not do this. So, you know, let's say you become a parent. You're very excited about your child, and you obsessively measure your child's height every month for the first, I don't know, 10 years of his life. Okay, and so, you know, every month you measure, you know, starting when, you know, whenever your kid can start standing up and being measured for height, we'll say there's a very strong linear relationship. Okay, and this is, we'll say, from age 2 years old to, you know, 4, 6, 8, 10. Okay, so you go, oh wow, strong linear relationship. Okay, there was never a time where the kid got shorter. Okay, keeps going. All right, now this would be ridiculous, but what if you're like, oh, okay, now I've fit a linear regression model, and based on my linear regression model, by the time this child is 40 years old, he will be, you know, 20 feet tall or something. Okay, so, you know, at age 40, you know, we would predict. So at age 40, we would predict a height, I don't know, of something ridiculous, right? I don't know, 20 feet or something. I'm just making that up. Okay, and we would say that that's stupid. Don't do that. But so it's obvious for, you know, age versus height. We know that this relationship doesn't hold. That at a certain point, the it kind of evens out, right? We know this, and so we know not to do this. But people like to do stuff like this, all right? They say, oh, well, look, we have this linear model. It's held true for every single month for the past 8 years. Therefore, in the future, this is what the future will look like, okay? We don't know what the future looks like, okay? Nobody can predict the future. That's the truth. And so, this is where we've collected data, right? This is up to this is the region where we've collected data. So we have data here, and we have no data out over here. Okay? So once you have no data, you really have no idea what's going to happen. It could rocket up, it could settle, it could dive down. We don't know. It could go in all sorts of directions. If you have no data out there, you have no idea what's going to happen. So don't do extrapolation. What you can do, you are allowed to do interpolation. Okay, interpolation is, let's say 1 month you forgot to measure your kid's height. Okay, and so you're missing data right here. Okay, so you have no measurement here. Okay, interpolation is saying, okay, well, I have data on this side and that side, therefore I can use my regression line to try to figure out how tall my child was for this month that I missed the data. Okay, you can do that. So if, interpolation is allowed, which is making a prediction for in between areas where you have data collected. Okay. Okay, so that's interpolation. You can do that. Extrapolation, don't do that. Okay. Yeah, I think that's about it for linear regression. So next week, so 1 week from today, you'll have a midterm exam. Okay, so the midterm exam will cover up through the stuff I've covered today. Okay, and then next week on Monday, we'll start Chapter 5, probability. You don't have to worry about Chapter 5 probability stuff being on the midterm. So you can put a little star in your notes here to say you've got to learn up to today's content for the midterm exam. Okay, we'll end a little bit early today, and so have a great weekend, and we'll see you guys on Monday.